NEMA, the National Electrical Manufacturers Association, has established dimensional specifications for stepper motors, as shown in this slide. The numerical size of the motor defines the full width of the square motor face in inches, the A dimension shown in the diagram. A size 11 motor has an A dimension of 1.1 inches, or 28.2 millimeters. A size 14 motor has an A dimension of 1.4 inches, 35.2 millimeters, and so on. The B dimension shows the distance between the mounting holes, and the C dimension shows the threaded hole size for mounting screws. The D dimension is for the diameter of the shaft, which may have a flat on it for attaching a pulley or gear. The length of the motor is not covered by the NEMA spec, and companies vary it to optimize their motor torque speed curves. The graph on the right shows the torque speed curve of a commercially available stepper motor. Like other DC motors, torque is highest when the motor is stopped and reduces as the motor speeds up. But remember that a stepper motor does not rotate continuously, so we measure speed in steps per second or steps per minute. You can safely increase the voltage to the motor and get more torque at a given stepping speed, but the increase in torque with voltage is not linear. In this motor, tripling the voltage gets you roughly double the torque. The motor specs on the right quote phase current, resistance, and inductance, as well as rotor inertia and motor weight. Large inertia and inductance values will require a high input voltage to obtain fast stepping speed. Holding torque is a very important spec for stepper motors, and so that is shown too. This motor is sold in different models. The different models have different lengths, which correspond to different lengths of the stator and rotor. Length would be the direction into the page in our plan views of the stepper motor. Adding length increases the electromagnetic attraction force between the rotor and stator when the motor is in a stable position. The permanent magnet rotor is larger, and there is more room to add coils to the stator phases. The phase resistance and inductance go up accordingly. The motor gets heavier by adding all that metal. Be aware of it if it matters to you. There are two ways to control the flow of current through the phase windings in stepper motors. In a unipolar drive, the current flows through the phases in the same direction each time they are energized. Half of the coil length used to turn a pole magnetic south, while the other half is used to turn the pole magnetic north. This simplifies the transistor circuitry. However, you get only half the current in a phase and roughly half the possible torque. In a bipolar driver, the full coil length is used to turn a pole magnetic south or north. The direction of current is reversed to accomplish the magnetic switching. The transistor circuitry is more complex, but using the full coil length creates the full torque output in the motor. This slide shows two simple ways to arrange the coil wires in a unipolar driver. Each winding has a tap in the center that connects to ground. In the 6-lead motor shown on the left, you energize phase 1, shown on the upper left, for one polarity, say magnetic north, by connecting the red wire to positive DC voltage and the black wire to ground. You reverse the polarity to, say, magnetic south by disconnecting positive DC voltage to the red wire and connecting positive DC voltage to the red/white wire. Current flows in the opposite direction in the winding, but only in one half of the total wire length in the winding. You energize phase 2 in a similar way, but using the wires shown on the lower left of the diagram. In that case, the green and green/white wires are for positive winding voltages, and the green wire is for ground. If you disconnect the black and white wires from ground, you can drive the 6-lead motor with a bipolar driver. In phase 1, you would connect the positive DC voltage to the red wire and the red/white wire to ground. You would get the full coil length, more current, and more torque that way. In phase 2, you would connect positive DC voltage to the green wire and the green/white wire to ground. In a 5-lead motor shown on the right, the center taps are connected to each other and to ground. You have one less wire connection. However, now you can use the motor only with a unipolar driver. This slide shows the coil winding in a 2-phase bipolar driver. It's what the 6-lead motor would look like if you disconnected the black and white wires from ground. Now you need only 4 leads to run the motor. None of the leads are common. All of them are connected to an H-bridge transistor or to a commercial driver chip that performs the same function. This slide shows the current flow through a winding for a unipolar versus bipolar driver. Typical values of resistance and inductance are shown. In a unipolar driver, current flows through the winding to a power transistor and then to ground. Turn the power transistor on and current flow starts. Be aware that when you turn the power transistor off, you risk damaging it when the voltage rises on the input end. You will need extra circuit protection with this simplistic design. In a bipolar driver, current flows through the winding in either direction. In theory, you can sequence the transistor operation in any manner. In practice, you must make sure to avoid turning one of the transistors labeled with 1 on before the other one labeled with 1 is fully off. The same goes for the transistors labeled with 2. Otherwise, you will send 25 volts through the low current paths of the 2 transistors labeled 1 or the 2 transistors labeled 2 and damage them. The power transistors have a certain amount of capacitance in them, and you must wait a certain amount of time for the capacitance to discharge when you control this circuit. Before you think that using a stepper motor will solve all your problems, let me warn you about a few things. Stepper motion can be jerky at low speeds using simple control methods. You can smooth out the motion by using complex motor control firmware, but it takes a lot of time and patience to write this code. Torque output varies throughout the step. This is known as torque ripple. Do not use stepper motors for loads with varying torque or with significant mechanical backlash. You won't be able to control the motion very well. Some other issues with stepper motors include these. There is a larger amount of rotary inertia in the rotor compared to other DC motors, and torque is relatively smaller too. From freshman physics, yet again, angular acceleration is equal to torque divided by rotary moment of inertia. Hence, acceleration to maximum speed is slower in stepper motors than other DC motors. Stepper motors are designed for low speed operation. Maximum speed is limited by the high inductance in the stepper motor. This comes from the fact that the electrical time constant is linearly related to inductance, and a high time constant means it will take a longer time to ramp up the current in the coils to their peak. Not only that, but you have to wait sequentially for the current to ramp up and down in each coil as the motor steps. This is not a big problem if you only want to move at 10 to 20 steps per second. However, if you try to move at 1,000 steps per second, you will find that the inductive time constant will prevent you from doing so. This is very different from brushed and brushless DC motors, where you have only a couple of coils that need to get energized when you turn on the motor. These motors will accelerate much faster than a stepper motor can. Let's recap. Now you understand details about the electromagnetic aspects of stepper motors. In the next video, we will teach you about commercial stepper motor driver chips and packages.